Welcome everyone to today's online seminar. Firstly, I'd just like to thank Aberystwyth and Queen's University Green Fund for the Zoom license. So today we are very pleased to welcome David Timmins, who is a lecturer in space weather and space systems at the University of Birmingham. David completed his PhD in 2018 and continued on into a postdoctoral position at the University of New Brunswick, where his research focused on the development of E-CHAIM. And I'm sure David will be telling us more about E-CHAIM in the seminar. His PhD work had been highly recognized with numerous awards, including the C. Young Scientist Award. Since joining the University of Birmingham in 2020, David continues to expand E-CHAIM and focuses on understanding interactions between our ionosphere and the atmosphere. So we're very pleased to have you here today, David. I'll hand over to you now. Thank you.
Hi. I guess this talk will be bit of a kind of a walk through how I guess a contract that we ended up having with the Defense Research and Development Canada led us to eventually develop this empirical Canadian hierarchic ionospheric model, or E-CHAIM, and just kind of go through some of the I guess user requirements that kind of framed a lot of the choice of methodology that we ended up going with. So just a quick outline. I'll do a really quick overview of the system we want to model, the ionosphere. I know the vast majority of you are already aware of how the ionosphere behaves and what it looks like, but just in case, I'll give a quick overview. Then I'll talk about the user, or in this case, Defense Research and Development Canada, and their requirements and their use case. Before talking about some candidate models that we were originally considering, or that the client was originally considering, before having eventually decided to just build one ourselves. And then we'll go through some progress since the original delivery of the model and some ways that we can move forward past where we are currently. So the ionosphere is a layer of the upper atmosphere, or an ionized layer of the upper atmosphere between about 80 and 1,000, 2,000 kilometers altitude. It's formed predominantly by photoionization or at high latitudes by collisional ionization of the upper atmosphere. And by virtue of it being an ionized plasma, it's highly coupled to the Earth's magnetic field. This down here is just a little demonstration of what the vertical profile of the plasma density profile of the ionosphere looks like. So altitude, electron density along the x-axis. During the daytime, given by black here, you can see that the ionosphere is broken up into a number of different layers. The D region here is the lowermost layer, mainly contributes, or is the main contributor to high frequency or absorption at high frequencies. The E region and F1 layer above that are mainly components of molecular ions like N2+, O2+, NO+, and so on. Above that, you have the F2 peak that has a peak density, we call it NMF2, and a peak height we call HMF2. And this layer is predominantly made up of atomic oxygen ions. Above that, we have an exponential decay that eventually transitions to a hydrogen and helium ion-dominated plasma. At night, given by the red here, you can see that the lowermost portion of the ionosphere rapidly recombines in the absence of photoionization. And so you're only left with really the F region atomic oxygen ion plasma environment. The ionosphere is also heavily driven by solar activity, where the dashed line here is solar minimum and the solid line is solar maximum. In terms of horizontal structure, and I'll only talk about high latitudes, this is just a representation of the log total electron content, or the integrated vertical electron density of the ionosphere above 50 degrees north geomagnetic latitude. well, actually 45, I think, in this case. But regardless, so at high latitudes, we expect there to be, a main ionospheric trough given by this region of depletion here, caused by the stagnation of plasma to the night side due to high latitude convection. We expect to see an auroral oval associated with the auroral particle precipitation that predominantly causes enhancement in the E region, but also contributes to the ionization budget of the F region. And then we expect to see, at least during most of the year, a polar hole in the polar cap where heating in the auroral zone due to Joule heating and neutral collisions results in significant outflow and also causes the scale height in this region, or the thickness of the ionosphere, to be substantially larger than the ionosphere in the neighboring subauroral and mid-latitude regions. So that's kind of what we expect the electron density in the ionosphere to look like. But I guess who cares? Who cares about the ionosphere? I'm only going to talk about kind of two use cases here, but ultimately there are a number of different reasons to have an interest in the ionosphere. One of those is for global navigation satellite systems like GPS. As their signals propagate through the ionosphere, the signals can experience range errors that eventually translate into errors when you try to triangulate your position. Also, irregularities in small-scale structures in the ionosphere can cause the signal to be scattered or diffract, resulting in a loss of signal integrity, eventually a loss of signal or loss of the ability of the receiver to track the signal, knocking out your GPS. By the same type of mechanisms, you can also get distortion in radio telescope imaging, which is, I think there are a few people in this community that work with LOFAR to that effect, so I imagine they can talk about it more than I can. But the main point of interest that my client in this case was interested in was the fact that the ionosphere can serve as a medium and reflecting surface for HF radio communications and remote sensing. So if you propagate, so this is just, I guess, an example here of the plasma frequency profile, or effectively the electron density profile of the ionosphere, given in vertical here over some cross section looking northward. If you propagate a signal upward, or an HF signal upward into the ionosphere, it'll get reflected at the point where the signal frequency is equal to the plasma frequency, or where the plasma frequency is proportional to the square root of the electron density. If you transmit a signal that's at a higher frequency than the maximum plasma frequency of the ionosphere, it just penetrates through. If you propagate a signal obliquely, you get the same type of thing. You do get reflection, but at the point where the plasma frequency is equal to, or the signal frequency is equal to the plasma frequency multiplied by a secant of the elevation angle. Regardless, what this does is this enables us to use signals in the HF band between 3 and 30 megahertz or so to get communications or to remote sense targets at very long ranges. So we can use the ionosphere effectively as a mirror to bounce our signals off of, to see past the horizon that you can see curving away here at the bottom of this plot. This phenomena, I guess, enables a certain type of radar technology called over the horizon, or over the horizon radar, where, again, we use the ionosphere to reflect off of, where kind of conventional radar might be limited to ranges of a few hundred kilometers. Over the horizon radar can detect targets at thousands of kilometers of range. And so if you're interested if you're interested in monitoring a very remote location where you don't have much ground infrastructure to deploy a bunch of radars, over the horizon is a I guess an attractive choice for remote sensing those environments, in this case tracking aircraft. So this brings me to my client, or the person we were doing this original work for, which is Defense Research and Development Canada. They received some funding from the Department of Defense to test whether or not over the horizon radar can be applied successfully in the Canadian Arctic. because of the requirements on, or because we're bouncing signals off the ionosphere, if you want to reconstruct a position from, I guess, an image that you get from this, you need a really accurate ionospheric model to kind of to do that reconstruction. I guess I want to say, so there are a number of reasons why using over-the-horizon radar at high latitudes might be challenging. The biggest one being this kind of requirement for an accurate ionospheric model. So you need an accurate ionospheric model to reconstruct the position of a target, this so-called coordinate registration. You also need a reasonably good ionospheric model to do what's called frequency management. It's how it's selecting what frequencies you need in order to surveil a particular region of interest. And you also need it for system design, particularly when we're talking about high latitudes where the plasma frequencies are quite low. So the operating frequencies that you might be working at would be rather low. And so it puts a requirement that or puts some constraints in the system such that you need to work with, bigger and more complex hardware. There are other challenges like auroral clutter and clutter from the F region that I'm not going to talk about here, but they're also a substantial challenge. So our main kind of priority was in this component here, coordinate registration, frequency management, and system design. And so we were given a set of requirements by DRDC in order to achieve, or I guess to meet their obligations. And those requirements can be split into two sets, pre-operational requirements that mostly have to do with system design and preliminary coordinate registration development, or frequency management system development. And then operational requirements that have to do with coordinate registration and then more operational frequency management. So for the pre-operational requirements, they set us out to develop or to find or develop a climatological model or a model that has climatological performance on the order of 1 megahertz or so. So the average monthly diurnal variation needs to be accurate to about 1 megahertz. It must be compatible for use with magnetoionic ray tracing, which ultimately means that it needs to be reasonably computationally fast, and it needs to produce electron density that's continuous and differentiable. The model needs to be self-updating, and that just was ultimately because they don't want to have to, go looking for indices or whatever to drive the model themselves. They want to just work, and it must be able to operate on a laptop. And this restriction is kind of more relevant to this operational requirement problem, but still something to consider in these pre-operational requirements. So what I'll be talking about today and what E-CHAIM was mainly developed for was to meet these pre-operational requirements. We have developed a assimilation system that's designed to meet these operational requirements as well, but I just won't have time to talk about them that much. Ultimately, this restriction to run on a laptop, along with the requirements for this to be real time and to have pretty good accuracy and time resolution, puts a really significant constraint on the type of data assimilation system that you can build. And so that's just a story for a different time, I guess. So the first kind of candidate that you might consider when wanting to do this type of work, and this is usually the place everyone starts from, is the International Reference Ionosphere. It's an empirical climatological model. It's recognized by the International Standards Organization. It's just kind of your de facto choice. However, it has a number of challenges that make it both unsuitable for high latitudes and in general for this type of application. One of those is that if you just take a cross section, you choose 150 kilometers altitude for all longitudes at a particular latitude. This is the electron density profile that you'll get out. And you'll notice these discontinuities here and here. So the ionosphere, the F1 layer in the ionosphere isn't always there. And so to kind of deal with that, the IRI has a trigger internally where it decides when the F1 layer is turned on and when the F1 layer is turned off. And this trigger depends on local time, effectively, and latitude. And so what ends up happening is if you transition from a region that doesn't have one F1 layer to one that does, you get severe discontinuities due to the discreteness of that trigger. You get the same type of problem if you just look at a single location in space and then look at the diurnal variation, and you can see again these discontinuities, which are problematic if you're trying to calculate Dopplers or something. But regardless, so this is problematic, but usually, you know, people that use this type of thing will just smooth these out and pretend that they don't exist. Another thing that usually I guess the HF community is figured to do is the IRI also has a number of discontinuities in the derivatives or the its vertical gradients. So if you look at the electron density profile from the IRI given by this guy here, you can see there are a number of piecewise continuous sections that make up this profile. And at the transitions between these continuous sections or these pieces, you get these discontinuities in the gradients in the vertical. They can be a bit problematic for ray tracing, but again, most people will just kind of smooth them out and be done with it. So really, just kind of quality of life problems, not necessarily things that are too difficult to get around. One thing that is problematic, and particularly for high latitudes though, is that this is the peak critical frequency of the ionosphere from the IRI or the FOF2. So the IRI by design has actually suppresses out the horizontal variability of its electron density at high latitudes. It's had to do with some problems when they originally fit the thing. And so you end up with the high latitude region looking just like effectively solar zenith angle. There's no high latitude features that you traditionally expect, you know, auroral oval, main ionospheric trough, borehole, anything like that. And so that's a problem. We generally want to have at least the basic climatological structures of the high latitude ionosphere when we're determining whether or not a system can actually be deployed to a region. But the biggest problem, those are all kind of quality of life things you might be able to kind of get around, but the big issue is that ultimately the IRI doesn't meet our performance requirements. Within the poor cap, we have errors in climatological FOF2 in excess of 1.5 megahertz. And that exceeds our minimum threshold that we need in order to meet the requirements of the client. So IRI is out. There are a number of other issues like the climatological total electron content from the IRIs has errors in excess of 15 tech units sometimes. And if you're, I guess, familiar with total electron content at high latitudes, this is a boatload. This is effectively, you know, 50% of your total electron content. And you can also end up with errors in the height of the ionosphere by 30 kilometers or so. So we might instead opt to use physics-based models, which are capable of resolving much smaller scales than those available to empirical models. And I have no question that physics-based models should have roughly the right horizontal structuring that we expect at high latitudes, perhaps not quite to the right magnitudes. But they're computationally slower than empirical models. And unfortunately, they've traditionally not performed quite at the level of even the IRI. And so it's unlikely that they would actually meet our performance requirements for this particular application. On the right here, I just have a nice little figure from Shim et al. 2018 from the CCMC, where they took all of the CCMC electron density models and compared them to ionosphere measurements at a number of locations during some geomagnetic storms. And what they ultimately found is that in terms of the RMS error or the absolute RMS error given in blue, and the error or the RMS error of the models in terms of their ability to represent the variations in electron density during storms, the IRI actually managed to outperform virtually all of them or all of them virtually all the time. And one of these is actually a data assimilation system, which is a bit troubling, but I think this has more to do with the the manner in which it's implemented at the CCMC rather than the simulation system itself. Anyway, so these aren't performing at the level of the IRI. It's very unlikely that they'll meet our requirements. So we're not really inclined to use these physics-based models either. So that leads us to build the system ourselves. And so we started making motions to develop the empirical Canadian hierarchic ionospheric model, E-CHAIM. For some reason, I have something in my throat today. I don't know what it is. So we ultimately opted to go down the road of the empirical approaches, mostly because for computational speed, and again, the accuracy seems to be just easier to achieve with an empirical approach. So in order to do that, though, we need to start with getting a bunch of data. So the first thing we did is we gathered about 28 million ionospheric observations from about 80 ionospheres around the domain of interest, which is above 45 degrees geomagnetic latitude. That spanned between 1931 and 2016. So the red dots here are the distribution of those ionospheric observations over that time. Actually, this red dot here was actually on an iceberg, as well as this one here that actually circled around in the Arctic Ocean quite a bit. This is just a snapshot at one time. But anyway, so ultimately, we have a pretty good coverage of these ionospheres, and they give you the electron density profile from the E region up to about the F2 peak of the ionosphere. Depending on how old the ionosphere is, some of the older ones only provide peak density and peak height. So that covers us for the bottom side. For the top side, we look to inquiry and scatter radars, radio occultation satellites, and topside sounders. Inquiry and scatter radars get you the electron density profile, depending on the mode, from the D region all the way up to the lower top side. Radio occultation measurements get you the same range, but they have some caveats to their application to lower altitudes, so below the F2 peak, so we didn't use it below the F2 peak. And then topside sounders, which are ionospheres mounted to satellites looking down, that give you the profile in the top side down to the F2 peak. So this plot here is just a demonstration of the coverage of those measurements used to represent the top side of the model. Once we had our data set, we had to decide on how to, I guess, parameterize the model, how to define the model. And that begins with the vertical structure. And I apologize for this terrible slide that is very uninformative. So like we might be tempted to do what the IRI did, but then we have those quality of life problems that we saw before, those piecewise sections and a trigger for the F1 layer. And it just wouldn't be particularly a good idea to go down that route when we have an opportunity to build something that doesn't have those problems. One route you might think to go down is to instead model electron density as a sum of different layers. So a Chapman function for the E region and for the F1 layer, and then for the F2 layer, and so on. But what ends up happening when you go down that approach is that the F1 layer is actually a very subtle feature that doesn't really lend itself to being pulled out well with least squares. And so very often it gets lost in the noise. And unfortunately, the F1 layer, while it may be a subtle feature in electron density, is actually a really important feature for radio propagation, because radio propagation doesn't just depend on the electron density, it depends on the derivatives of the electron density. And so we need to kind of consider the representation of that F1 layer, or consider an approach that better qualifies that F1 layer. And so one of the ways to do that was to, instead of thinking about things in terms of electron density, to just say, well, we're going to model everything as this kind of semi-Epstein layer given here, where instead of bothering to add in a bunch of different layers and things like that. We'll just vary the scale height or the scale thickness of that single layer with altitude instead. And the advantage to this is that we can effectively transform our space from an electron density space into a scale height space. And to be clear, this is not the physical scale height. This is a scale thickness. It's an arbitrary concept that's specific to this Epstein layer here. But ultimately, when you do that, this electron density profile here that has a relatively subtle F1 layer structure here has, in the scale height domain given down here, a discrete peak associated with the F1 layer. And so this scale height actually ends up being sensitive to the derivatives of the profile, as well as the absolute electron density of the profile. And so it allows us to more easily pick out and add weight to the derivatives as well as the absolute electron density when we do the fitting. So ultimately, E-CHAIM is not really a model of electron density per se. It's a model of this kind of scale parameter here, as well as NMF2 and HMF2, because we need those to transform into that space. Yeah, so this leaves us with a number of parameters that we need to define the vertical structure of the model that we then need to specify horizontally and in time. To do that, we didn't really do anything particularly clever. We just used spherical cap harmonics given here, where this is your longitude coordinate and this is your latitude coordinate. Where the Gauss coefficients of these spherical cap harmonics are expanded in terms of a Fourier expansion in day of year to get us our seasonal variability. And then these are in turn also forced by these two forcing terms here that depending on which parameter we're modeling, we choose appropriately. So for the NMF2 model, these forcing terms were F10.7's flux smoothed over 81 days, and the square root of it. And the reason for adding this, effectively the square root term, is to account for the fact that electron density tends to saturate as you get to very high solar activity levels due to a feedback with the thermosphere. And so generally we need to account for that when we're designing our NMF2 model. Similarly, for like the thickness models, we do have still have this F10.7 term, but we've actually switched out the second term for a term in AE index to account for the heating effect on the thicknesses at high latitudes, which ultimately tends to be about of the same magnitude as the solar activity forcing. In terms of diurnal variability, HMF2 and MF2 are the peak height and density of the ionosphere defined as 24 different models, one for every UTC hour. We had 28 million observations and we couldn't fit it on a computer with 68 gigs of RAM, so we decided to split up into 24. The top side and bottom side models, however, had substantially less data. So what we did is we just switched out this longitude term for magnetic local time and conflated our conflated our local time and geographic variability together. Ultimately, once you do that, you fit everything, you do your regularization with a subset of that data set. We also reserved a certain number of stations, or 4 stations in this case, that weren't included in the model fitting, so that we could do some additional validation later. And so if you look at in the polar cap at Resolute, we can plot out the monthly median diurnal variability. So this is time of day and local time. This is day of year here from an ionosonde given in this column, and then from E-CHAIM and the IRI. And you can see in general, we do a pretty good job at capturing the seasonal and solar cycle and diurnal variability in the peak density of the ionosphere at this particular location, especially when you add in the IRI for context, which is not doing so great. In terms of our client's requirement for climatological performance better than 1 megahertz, These are the RMS errors between the model and ionosphere observations from the IRI and dashed lines here, and then from E-CHAIM in the solid black lines. You can see in general, we're nowhere close to being above our, or we beat our one megahertz requirement quite well, universally, both in the polar cap at Resolute and Alert, as well as in the Auroral Oval, where Cambridge Bay is at the poleward, or the poleward edge of the Auroral Oval, and Eielson is well within the Auroral Oval. And you can also see that the performance between the two models, the IRI and E-CHAIM, tends to converge a bit as we start getting into the Auroral Oval and below. And this is kind of what we expect. The IRI is a pretty good model for mid-latitudes, so it's good to converge to it at your lower boundary. In terms of horizontal variability, this is the peak electron, or the critical frequency FOF2 from E-CHAIM for the same time that we showed before from the IRI, where you can see, hey, we've got a main ionospheric trough. It's a bit wider than it probably should be, but it's a statistical model, so it's going to get blurred out, or thin structures will get blurred out, and we're limited to the resolution that we have available from the limited data set that we have available. But it's there. We also have our oval, polar cap here, and also this little extension of the daytime electron density maximum into the higher latitude region associated with convection. So this consistent, looks good. We at least have all of the features that we were hoping to have at high latitudes climatologically. Another thing, talking about the thicknesses of the ionosphere, as I mentioned before, we expect the thickness of the F layer, given here, to be at a maximum within the polar cap and Auroral Oval associated with heating in that region. And that's exactly what we see. And what I'm going to show here is just a quick movie where you're going to see, I think, 192 hours of thickness variability over our domain. This is magnetic latitude, and then this is magnetic local time, where this is midnight, this is morning, and this is noon. You can see there's a geomagnetic storm here that causes substantial enhancement in the thicknesses. Then it relaxes back, and then you get another geomagnetic storm towards the end of the period that causes another enhancement. I'll play it again. So we have this oscillation associated with UT variability, and then enhancement due to the geomagnetic storm. And then a gradual recovery as things go back to normal, and then a secondary enhancement as the storm begins again at the end of the clip. Or another storm begins at the end of the clip. So that's good. We've met all of our obligations to our client. We've met what their expectations were, so that's good. But we also wanted to see just how far we could kind of push these simple empirical approaches. And so while we can't get patches, we can't get tongues of ionization, we can't get mesoscale structures like that, because it's just not going to be possible with these types of techniques. What we can get is the large-scale ionospheric response to changes in thermospheric composition during geomagnetic storms. So these negative ionospheric responses that we tend to get associated with geomagnetic activity. So here we have electron density, peak electron density from Resolute and Pond Inlet, both within the polar cap, from the ionosomes in black, E-CHAIM in blue, and the IRI in red. And you can see in general, E-CHAIM does a really good job at tracking the pre-storm electron density, and it does a good job at tracking the negative ionospheric response to this particular geomagnetic storm, which only is only about a KP5 storm, but it's just a demonstration. Of course, this is a really good example of how well this performs, and it's not necessarily indicative of overall, or how it does overall. So what you can do is you can take electron density from some of these ionosomes over a year, remove the 30-day trend from each of them at each UTC hour, And what you're left with is the anomaly of these anomalies, which are the monthly variability that exists in the observations. And what you'll see are these bands, and those bands are all geomagnetic storms, particularly the large scale negative ionospheric responses to those storms. And the main point here is you can do the same thing for the model, and then this is what you get, where you can see we do get those bands. However, the amplitudes of the responses are substantially muted from what we see in the actual observations. And it turns out that we're only capable of getting about 25% of the variability associated with geomagnetic storms with this really simple scheme. But it's a very simple scheme that gets you 25% of the variability at virtually no cost. So that's about the limit of what we could do without starting to go into data assimilation. Another thing we've done is we've looked at the effects of shorter time scale solar activity driving. So changes in EUV flux on solar rotation timescales. So the black here is pass averaged electron density from DMSP at about 800 kilometers altitude. The red is the IRI. The green is the normal E-CHAIM. And the purple is the EUV flux scaled to arbitrary units during this period. And you can see that there are substantial variations in the topside electron density due to these variations in solar activity. And if we just change the solar activity driving in E-CHAIM to, instead of being that 81-day smooth stuff, to daily or weekly F10.7 flux, we get the blue curve, where you can see we've actually been able to recover a lot of this variability on these monthly or so timescales, which is great. Again, costs us very little, and we get a significant improvement in performance. Another thing we've done since initially giving this off to our client was we've added in an auroral E region. It's a sad thing to call yourself a high latitude model if you don't have an auroral E region. And so we've used a Fang et al. Parameterization with these old Gledhill effective recombination rates combined with an assumption of photochemical equilibrium to create perturbed electron density associated with particle precipitation at energies below about 30 keV. This is just a demonstration of what that looks like. So that gets us from the blue profile here, which is our standard E-CHAIM, to the dotted red profile here, where the black line is the incoherent scatter radar data from that particular day and period. This is actually a best case scenario in this case. We've driven this with measured auroral energies and fluxes, or mean energies and fluxes from SUSY on the DMSP satellite. But it's just to give an indication that this rather simple parameterization can get us an acceptable auroral E region, at least from a simple empirical approach. We then have our own model of these energies and fluxes, which is just purely statistical, and incorporate that into the model. And then we can compare to poker flat incoherent scatter radar electron density profiles, altitude, time of day in May 2016, to what we get from E-CHAIM, where you can see we've got these nice little auroral enhancements down here in E-CHAIM that correspond well to the enhancements that we're seeing in the Pfizer data, although they're a bit more smoothed out and they can't quite get to lower altitudes due to the limitations on the energies we're sensitive to. Overall, this is just the center here is just a plot of the RMS errors from normal E-CHAIM in black, and then the E-CHAIM with this precipitation module included in blue for virtually no geomagnetic activity, modest geomagnetic activity, and then strong geomagnetic activity down here. You can see in general, obviously we get an improvement from incorporating this particle precipitation scheme into the model. And this is just submitted to Space Weather recently, so I'll send you the paper if you'd like. So in general, we get a significant improvement in our performance at E-region altitudes by incorporating a fairly simple precipitation scheme into the model. So ultimately, we've built a climatological model for high latitudes that meets our client targets, and we've added in a bunch of other smaller kind of quality of life improvements to the model to try and squeeze out as much performance as we can possibly get from these really rather simple empirical methods. There's still some things that we did want to do. We want to also add, or expand our range of energy sensitivity in the precipitation module to greater than 30 keV fluxes or energies, sorry, using POSE MEPED. We also want to include solar energetic particles, possibly through Neil Rogers parameterization. And so this is, about the limit of what we'll probably ever be able to do with this empirical model, but that'll probably be the end of the road. Which will bring us to data assimilation, which is ultimately where we need to go in order to meet the operational requirements that I talked about before. And we developed our own system that assimilates ionosomes, GNSS, real occultation, SUSY ultraviolet imager data, and altimeter data. And it ends up, again, meeting those requirements that I stated before for operational use. The problem with this, of course, is that this is a simulation system built on an empirical model, E-CHAIM. And so because of that, it has a limited forecast capacity. Effectively, you're operating at persistence and forecast. So we'd like to ultimately add in a bit of physics or specific components of physics to try and improve our forecast skills, specifically including semi-Lagrangian advection into the model or into the assimilation system, and then expanding our data set to include ground scatter from SuperDARN and variometer absorption data. Anyway, that's it for me. Sorry about the bit of a rush at the end there. But if you're interested in using E-CHAIM, it's openly available online at this link here, and I can send you the link if you'd like. And we provide distributions in C, MATLAB, and IDL, all source code, so you're happy to have that if you'd like. We also provide the assimilation system and interface tools in order to use the output from that system as well. Thank you.
Thank you, David. That was really interesting. So we have one question coming straight away, but yeah, so now we'll do questions. So if you have one, type it in the chat, or if you'd like to ask it directly, just put your hands up and we'll be keeping an eye on that. So the first question comes from John, and John is wondering if there is a Python version in the works.
Yeah, so we've wanted to. Like Michael Hirsch at one point was offering to port it for us, but then he never followed up. Effectively, the easiest thing to do for Python would be to wrap into the C code. As far as I'm aware, that's not too difficult, but that's all we have planned at the moment. I think actually Mike Warrington, because he's actually been involved in some of the radio propagation side of this project. He developed a wrapper to wrap into the C code using Python. So you might want to talk to him. He might be able to help you out. It's tough enough trying to support 3 source languages. Adding in Python was going to be another mess. So
great. It says, thank you, exclamation mark. Was that Mike Warrington?
Yes, Mike Warrington. Sorry.
Okay. So Anasoyas asks, how does your H scale thickness relate to scale height, which depends on the neutral temperature?
Well, so again, as I mentioned, the scale thickness that I'm referring to is really just kind of an arbitrary. It's dependent on this semi-Epstein layer. It's not a physical principle. So in terms of its relationship to, say, like a Chapman scale height or a more physical scale height, it's actually about a factor of 2. They almost relate to each other by a factor of 2 linearly. But otherwise, again, there's no reason to expect that this would have a physical necessary or direct physical attachment, just by virtue of the fact that it's based on an unphysical function. If that answers your question, sorry.
Yeah, and so I hope that answers your question, but feel free to unmute if you want to discuss it further.
Hi. Yeah, if I could just ask, that means it won't include any thermospheric inertia.
No, so again, this is everything that we're getting, like in terms of this variability here, is actually just from an AE index. This isn't physical. This is all being driven by a relationship to AE index expanded in spherical cap harmonics and fit the data.
And so your aim is to match your the tech, and it's performing well, as you understand.
Oh yes,
Yeah.
in terms of the polar cap, I think in terms of climatological to electron content, we perform at, well, depending on the time of year and solar activity, better than 1 tech unit on the daily average to electron content profile.
And the 25% capture of the variability, how do you know it's 25%?
Well, I can send you the paper on that, but effectively that was quantified based off of comparisons to these ionosphere observations. There's quite a bit of math involved, and I don't have a blackboard, unfortunately.
No, sure.
But I'll send you the paper if you'd like. If
Brilliant.
That's of interest.
Yeah. Thank you very much.
Thank you for that question, Answer. If anyone else has one, please pop it in the chat or hands up. I think I've got everyone in the chat so far. I actually had, if no one's asking a question right now, I can ask my really basic one. I'm not so familiar with the ionosphere, so apologies in advance, but it was actually about this slide. So where you have like these red patches in the ionosphere data, and also you see enhancements in your model, they're from like storm times, right?
Yes, although we have to be a bit careful because so this is done by removing the 30-day smoothed electron density, or FOF2. So these are actually almost all negative responses from the climatology.
Okay.
So they're almost all negative ionospheric responses, but because we do a smoothing, we cut through the middle of them. So just be a bit careful that positive here doesn't necessarily mean that was a positive increase in electron density compared to the climatology. It just means that it could have been a very large negative response that got sliced through because it occurs over a course of a week.
Okay. Okay, I think I understand that.
Sorry.
That's okay. Now I was just interested because at these times where you see like the reddest values, there are also the times where you see like the bluest values as well, even compared to like the quieter times. And is that expected because of the slice through as you described?
Yeah, that's actually exactly what's happening. So in this particular case here, this is actually a 5 megahertz dip in peak critical frequency during this geomagnetic storm. It's actually a really cool, severe geomagnetic storm that I've been looking at for years and just never had a chance to actually publish anything on. But yeah, so it's a full 5 megahertz depletion and then gradual recovery. So the response you're seeing here is just being cut through the middle of that, unfortunately.
Okay, that makes sense. Okay, great. If anyone else has a question, ask it sooner. Otherwise, I'm just going to keep talking. Okay, the second question I had was when you compare like your Ionosphere data and the model, they match up like extremely well, like it's really impressive. So you said that there's still things that you want to sort of improve or continue to develop on the model. How will that improve like the model matching for certain times? Because where are the areas of improvement? Because the model looked like it matched so well for all different levels of geomagnetic activity.
Yeah, as I mentioned, this is a bit of a cherry-picked example, right? So be very careful with this example, and I'll be perfectly honest that this is a really nice one that I'm happy with. But you can go to maybe here. There are still some areas of difference. You can still see that we tend to kind of overestimate the electron or extend or bridge the semi-annual anomaly a bit at high solar activity here. You can see it, well, I guess the main improvements that maybe I included a slide on this and extra stuff at the end. Did I? No, I didn't. Sorry. The main area that we're actually having some performance challenges with right now is actually mid-latitudes, or the upper mid-latitudes, where we tend to underestimate electron content there. We tend to converge to IRI performance at that level, which is not great in terms of tech. And we believe that to be where, let's see here, you'd have to extend this out to lower latitudes, but we tend to be, I think, underestimating the thickness of the top side at mid-latitudes, and so that's causing some problems for us. The biggest thing, or the biggest challenge that I have with these empirical methods is that we're modeling everything as a separate component, and they don't communicate with each other. And so what can happen is you can have, well, we know at mid-latitudes we have an underestimation of NMF2 by maybe only 5–10%. But we also underestimate HMF2 by 5 or 10%, or well, 5% to 2% there. And we also underestimate the thicknesses by 5 to 10% there. And so what happens is if you look in the top side and compared to in situ measurements, we actually have more substantial errors in that region, because all of these smaller errors end up adding up together because of they're just interfering or destructively. And so ultimately to answer your question, this is a cherry-picked example. We do have some seasonal effects that we do need to repair, and we can do that with data assimilation. Those mainly have to do with atmospheric forcing usually, that we don't have any drivers of, so obviously we're not going to be able to get it. Things like sun stratospheric warmings and things like that.
Okay, great.
Sorry.
Thank
Long, gambly answer to a
That's really
question.
interesting.
I'm sorry.
Oh, there is one question. Sorry, I was taking over with question time. Mike Pinnock asks, for your client, I'm thinking that times when they can't make over the horizon radar observations because of enhanced D region absorption are important. You showed thickening of the ionosphere during storms, but how well captured is D region ionization? That's in the chat if you want to read it.
No, that's fine. The answer to that is, I didn't mention it here, but we did add in the Fury D region to this model. It's a quiet time D region model. So it's, take that as what it is. But the biggest thing that, and I mentioned it maybe at the end here, is that we don't actually have, flares or solar eject particle events, or so polar cap absorption in the model right now. And that's something that we're actively trying to pursue, even these higher energy precipitation effects that affect absorption in the D region. These are all things that we'd really like to pursue, and that's the direction we're going in. Now that we've dealt with the larger kind of ionospheric electron density side of stuff, now we're trying to focus in more on the absorption side of stuff in the D region.
Okay, great. I hope that answered your question, Mike, but feel free to, yeah, someone's giving the thumbs up, so I think it's Mike.
I can't see the chat, so I'm...
Yeah, I think that's, if anyone has a question, can you type it in quickly now? Otherwise, we might wrap up there. We had some really interesting discussion, so that was great. Nothing else has come into the chat, so I think we'll finish there. Thank you, David. That was a great seminar, really interesting, and I learned so much about the ionosphere, which I needed to. Thank you, everyone, for contributing to the discussion and the Q&A session. That's all for today. So enjoy the rest of your day, everyone. I'll circulate details about the next MIST online seminar, which is going to be on the 4th of May. So keep an eye on your inboxes for that. Thanks again, David, and thanks, everyone. Bye, everyone.